Let's dive right into this explainer and master the physics of light and energy for your grade 10 physical sciences exams. I'm honestly so excited to guide you through this because this topic literally illuminates everything around us. But before we get bogged down in the math and the textbook definitions, stop for a second and just ask yourself, what invisible forces are secretly passing through your body at this very second? Because whether you're sitting in a classroom, studying at home, or walking outside, you're constantly bathed in an invisible sea of energy. From the signals connecting your cell phone to the network, to the warmth of the sun on your face, it's all connected by one single fundamental physical phenomenon. Here's our roadmap for today. We'll quickly cover the invisible forces, wave-particle duality, properties of EM waves, the electromagnetic spectrum, calculating wave energy, and finally, penetration and dangers. Okay, starting with section 1, the invisible forces. Where exactly do these waves come from? Well, it all starts with electricity and motion. Now, the absolute crucial point you need to remember for your exams is that every single electromagnetic wave originates from an accelerating electric charge. That's the golden rule. If you take an electric charge, like an electron, and you force it to accelerate, meaning it speeds up, slows down, or sharply changes direction, it creates a ripple. Think of it like throwing a stone into a totally still pond. But instead of water, this ripple is traveling through the very fabric of space itself. Moving on to section 2, wave-particle duality, or two ways to understand light. What's really wild here is how physicists actually describe this radiation. For the longest time, the brightest minds in science argued endlessly over what light actually was. Is it a wave? Is it a particle? Looking directly at the exam guidelines, you've got to explain that it's actually both. Some aspects of electromagnetic radiation are best explained using a wave model, and some aspects make way more sense using a particle model. It's not just one or the other. We call this the dual nature of electromagnetic radiation. Think of it this way. The wave model shows continuous flowing waves of energy that can bend and interfere with one another. But then the particle model describes light as tiny, distinct, indivisible packets. So sometimes light acts like a flowing river, and other times it behaves more like a stream of tiny, microscopic bullets. If we're talking about that particle model, you absolutely must memorize this exact definition. A photon is simply a packet of energy found in light. That's it. When we say light is behaving like a particle, we're talking about these photons. Just imagine a photon as a microscopic little delivery box carrying a very specific set amount of energy. All right, section 3, properties of EM waves and how they actually travel through space. So how do these fascinating waves actually move? When not original electric charge accelerates, it creates an oscillating electric field. That changing electric field then creates a magnetic field perfectly at a right angle to it. And here's where it gets really cool. That changing magnetic field produces another electric field, and they just keep going. They propagate as mutually regenerating fields. And because they literally build each other as they go, they don't even need a physical medium like air or water to travel through. They can zip right through a total vacuum, like the vast emptiness of deep space. And they're doing this at a speed that is literally mind-boggling. In a vacuum, all electromagnetic waves travel at the exact same constant speed, the speed of light. We represent that with the letter c. And that number? 3 times 10 to the power of 8 meters per second. Guys, that is 300 million meters every single second. Which brings us to section 4, the electromagnetic spectrum, from radio all the way up to gamma. Now let's step back and look at the whole family of these waves, the electromagnetic spectrum. Even though they all travel at that same crazy speed, they definitely don't pack the same amount of energy. For your syllabus, you need to know how to arrange these from lowest to highest frequency. Down at the bottom, you've got low-energy radio and TV waves. Move up and you hit microwaves, infrared, and then that tiny narrow slice of visible light, the only part our eyes can actually see. Keep climbing and the energy ramps up into ultraviolet, X-rays for medical imaging, and finally, super high-energy gamma rays. Notice how each type connects to a very specific everyday use. Let's hit section 5, calculating wave energy, the mathematics of light. Now, I know the math can look intimidating, but I promise it's incredibly straightforward once we break down the variables linking speed, frequency, and energy. Step 1 is the wave equation. The speed of light, c, equals frequency, f, multiplied by wavelength, which is that Greek letter lambda. Step 2 brings in Planck's equation. This tells us the energy, E, of a single photon equals its frequency multiplied by h. Now, h is Planck's constant, a fixed number right there on your formula sheet, 6.63 times 10 to the power of negative 34 joules seconds. Finally, step 3 is the combined equation. Energy equals Planck's constant times the speed of light, all divided by the wavelength. So if you've got either the wavelength or the frequency, boom, you can always find the exact energy of that photon. And finally, Section 6, Penetration and Dangers, the real-world consequences of high energy. Those energy numbers we just figured out, they have huge real-world consequences. Based on the formulas we just learned, the higher the frequency of the wave, the greater its energy. And the golden rule here is simple. Higher energy means greater penetrating ability. A low-energy radio wave just washes right over you, completely harmlessly. But high-energy waves, they act completely differently when they hit solid matter. And yeah, that includes human tissue. This is exactly why your exam guidelines make a point of highlighting these specific dangers. Ultraviolet or UV radiation has enough energy to literally damage your skin. That's exactly why we wear sunscreen. Moving up, X-rays have even more energy and penetrating ability. They're super useful for seeing bones, but they pose a serious danger of internal cellular damage if we don't strictly control the exposure. And at the very top, gamma rays pack the absolute highest energy and extreme penetrating ability, making them incredibly dangerous to living things. So I'm going to leave you with this thought to ponder as you gear up for your exams. Every single time you heat up your lunch, scroll on your phone, or just step outside into the sunlight, you are actively interacting with mutually regenerating fields of electric and magnetic power. They're rocketing around at 300 million meters per second, acting as both a wave and a tiny packet of energy all at once. It's honestly like a hidden superpower built right into the universe. Keep exploring, lock down those equations, and stay curious.